Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to talk to you a little bit about linear power supplies, more precisely various integrated circuits and various solutions that we might employ in order to create a smaller voltage out of a bigger one by using linear circuits that are not LDOs. And I'm not going to discuss a lot about the intricate electronics details, because these are typically things that have been talked about in many videos on YouTube and articles on the internet before. Rather, what I would like to present to you are a few informations that are perhaps not so obvious, and I would like to basically analyze what are our solutions when we want to use such a circuit, a linear voltage stabilizer, from a perspective of the price, so from a financial perspective, and from other perspectives such as availability on the market and flexibility. Because honestly, these are things that are not really discussed in other videos. And I have to admit that these are things that I haven't even thought about so far until recently, when I had certain discussions in private with a viewer of my other channel where I speak on my language. And I realized that I kind of fell in the same I don't know if I should call it trap. Maybe trap is a bit too exaggerated, but anyway, I kind of fell in the same, let's call it trap for the sake of simplicity, but again, it's a bit exaggerated, of trying to see integrated circuits like LM317 as the go-to chip whenever we want something like this, whenever we want to accomplish such a task of obtaining a regulated voltage out of higher voltage that could be regulated or perhaps isn't. And well, actually, although I'm not saying that those would be bad solutions, and I'm gonna discuss about two of the most popular solutions when doing that, although those are not really bad, and they do come with certain advantages, they don't really make so much sense from other perspectives, such as the perspective of how flexible those solutions are. So this is what we are going to take a look at today, and I'm going to explain to you several smaller circuits, as well as a bigger circuit that I have made some small tests earlier on the breadboard. So yeah, we will basically take a look at the same things that you have surely seen on other YouTube channels, but from a completely different perspective. And I will also show you some things that I'm pretty sure you haven't seen on other channels, or if you have, then those were very, very rare videos about that. Anyway, before we move forward, please allow me to speak a few words and to thank my sponsor for this video, which is PCBWay. When it comes to various circuits that are more complex, manufacturing them can become more difficult at home. So luckily there are companies like PCBWay, a leading PCB manufacturer with many capabilities to help you build even your most difficult projects. You can easily get an instant quote for PCB manufacturing from the website's front page, upload the Gerber files, and have your PCBs created in just 24 hours. If you need more to get your project finished, they can also offer PCB assembly services with manufacturer direct pricing, so you can have your PCBs delivered with components soldered on. This way you don't have to do the tedious work yourself. But in the case that you do want to do this work and you just need the CMD stencils, they can manufacture these for yourself, so you can solder the components yourself. Finish your design in your favorite design software, upload all the necessary files to PCBWay, and you'll be contacted by one of their professional representatives after they manually review your project to offer you one-on-one customer service in order to make sure that your circuits get fabricated just the way you want. If you're building your circuit for a device that will need a case in the end, then they can also help you with that as well, offering you a 3D printing or injection molding services to have your custom-made plastic case, or perhaps CNC machining services to help you with a custom metal case. All you need to do is go to PCBWay.com, the link is in the description. Thank you PCBWay for sponsoring this video, and now let's get started talking with all the informations that I would like to show you in this particular video that, in my opinion, haven't been discussed before. So I thought about, you know, what are the situations when we actually need to have a power supply, no matter how simple or how complex. And honestly, I can only see two potential situations that are basically fundamentally different. The first situation is when you want to power a certain circuit that's most often part of a larger device. You need a relatively fixed output voltage, but it's not critical. It can, in vast majority of cases, it can vary by, let's say, plus minus 1%, 2%, 5%, sometimes even more. Your voltage is relatively high, so that's still part of the first situation. So let's say 5 volts or more. Honestly, I haven't seen so far any situation when I would want to use less than 5 volts. I know that there are some digital circuits that require 3.3 volts, but I haven't seen any use case, at least for what I do and for what I try to do in my projects and, you know, the projects that I show you on this channel. In the vast majority of cases, we need 5 volts or more. Within this situation, you also want the solution, basically the power circuit, to be as small as possible. One other thing that I haven't really written here because I forgot, but I just remembered, is that we are strictly talking in this entire video, basically we are strictly talking about the idea of buying components from the market in order to create such a power supply. Okay, we are not talking about using components that we extracted from older semi-broken devices, even though we could, but in the vast majority of cases those would basically present themselves as a third situation, because in the vast majority of cases we would not be able to salvage, to scavenge, I don't know how you call it, to recover components that are basically what we need for a power supply with integrated circuits. We would be able in certain cases to recover transistors and maybe some Zener diodes from some older devices, and we could in that case create a power supply circuit with those. But I'm not talking about those. I'm talking strictly from a perspective of us right now wanting to know what components should we buy from the market, preferably in large quantities, so we can just have them in the future, so we don't have to worry about them. Okay, so situation one was, like I said, you want a fixed voltage, but it can vary to a certain degree. You want to lower, you basically have a higher voltage and you want this fixed stabilized voltage to be lower than what you have on the input. So your problem is, okay, how can I solve this as quickly and as cheaply as possible, and preferably as simply as possible as well. The second situation, which basically requires a different discussion, and I will show you a different circuit for that, is the situation when you actually need a standalone power supply, either because you need it for lab purposes, like we are doing right now, you know, as passionate electronists, we need to have some lab power supplies. Or you need a standalone power supply for service purposes, like let's say you want to deal with repair, some repair work, you want to fix broken devices, you know, and you need a lab, well, yeah, essentially you would still need a lab power supply, but for service purposes. Or perhaps you need a power supply that has some special features for charging accumulators, or how you call them, rechargeable batteries, and so on and so forth. In those situations, you need to have both voltage and current adjustments. Okay, so you cannot have just a fixed voltage output and no adjustment whatsoever, no current adjustment whatsoever. No, you actually need to adjust voltage and current, and ideally you want to adjust them down to zero, which is something that many ICs can't really do for various reasons. But anyway, in this situation, complexity and size are not usually a problem, so you can live with a more complex and bigger circuit that will occupy more space, because again, we are talking about a standalone power supply. In the vast majority of cases, we are not talking about a circuit that you have to include in another device, right? So these are two completely different situations that basically point us in different directions. And now we will be discussing a lot about the first situation. Towards the end of this video, I will show you a circuit that I've tested earlier that caters to the second situation. Okay, so let's start with basically what everyone else is showing you, which again, they are not bad solutions, but like I said, we need to take a look at these solutions from a cost perspective, from a financial perspective, right, and from other perspectives as well, such as flexibility. For the sake of making myself understood, I will throw some prices per piece, per each component. The prices themselves as an absolute value don't really matter, because what I will show you is the fact that we have some alternatives, some options that are actually cheaper than the most popular one. So what we will care about is basically the ratio between those prices and those other prices. Okay, so I have gone earlier on my favorite electronics distributor, and I have taken the absolute cheapest price for every component that I'm going to be presenting to you in the following moments, and I have placed those prices here in my currency. Okay, I haven't bothered to change it in dollars or in euros, because again, we do not care for absolute prices. Your prices will definitely be different based on where you live, based on what online shop you prefer shopping from, and based on a whole bunch of other things. Okay, so when you see lei here, do know that it is my local currency. For the sake of making things clear, okay, I have placed here the fact that right now, today, as I'm making this video, $1 is 4.58 lei, give or take. I've actually rounded it to 2 decimals because it was with 4 decimals and it just doesn't matter. This doesn't make sense anyway. And €1 is 4.94 lei. So basically, you know, if you really want to know each individual price, how much it is, just divide it by some 5-ish and you will get the price in dollars and in euros. Anyhow, let's get started. So whenever we think of linear power supply with at least with adjustable voltage, most often we think at LM317, right? I mean, this is probably the most popular integrated on the market so far. As far as I know, is the most modern one that was invented relatively. It's relatively new. It was invented relatively close to our times, even though it's quite old by now. But anyway, this is the kind of integrated that appears in many circuits on the internet, both on websites and in YouTube videos. Nothing wrong with him, but like I said, there are various alternatives that are actually at least equally better from a technical point of view and definitely better from a financial and flexibility point of view. So LM317, actually there are two different families. One family is 117, 217, 317. These are positive voltage regulators. The number in front designates the temperature range that they can work. Anyway, I'm not gonna go into great details about them. There are also 137, 237 and 337, which are basically equivalent, but for negative voltages. We're just gonna discuss positive voltages today for the sake of simplicity, okay? What are the pros of using such an integrated circuit? Well, it's relatively simple to use. I mean, the absolute minimum required components are the integrated himself and two other resistors that basically set the output voltage based on their ratio and a certain formula. Again, I'm not showing full circuits and full details because those don't matter here. So this is a relatively simple to use solution. I would say it presents a small physical space. I mean, it doesn't... creating such a linear power supply, a linear circuit, powering circuit, doesn't take a lot of physical space inside your device, and of course that's an advantage. And let's say I wouldn't consider it an advantage, but neither a disadvantage. The voltage is adjustable from 1.25 volts, give or take, up to some, I don't know, 37, 36 volts, something like that. I don't remember exactly. I do know that there are some high voltage variants out there on the market, but they are quite rare as far as I've seen them. And they can go up to, I don't remember, 45 volts or something like that. Anyway, quite a wide voltage range, but the fact that you cannot go down to 0 volts sometimes is a problem, okay? Maybe not that big of a problem. I've set it to being an advantage here because I will show you the second most popular version, which actually can go down to only 2 volts or 2.5 volts, something like that. So that's obviously worse than 317. But anyway, most of the times it wouldn't be a problem that with 317 we can go down to only 1.25 volts, but sometimes this can be a problem. What I would say there are clear disadvantages are this integrated price. I will keep saying chips from now on because saying integrated circuits is a bit long, so it doesn't make sense. So I will just keep referring these to as chips. So these chips come actually in two different versions. I mean, each code comes in two different versions. Right now, there is a version that can go up to 100 milliamps of current maximum. It's in a very small plastic package that is similar to small power transistors. If you buy 100 of these at once, they will cost you 0.93 lei a piece, which is basically something like 20 cents, give or take. If you want to go up to 1 amp or maybe even 1.5 amps, I know officially it says 1.5 amps, but I don't know if that particular variant can go up to 1.5. I would say let's stop at 1 amp. There's also the TO 220 package variant that of this IC that costs about 1.94 lei, so more than twice the price of the small power one. Okay, yeah, it is true that you basically have a power supply, a pretty decent power supply. I mean, probably most circuits will not need more than 1 amp. And you have a pretty decent power supply with very few components. But still, 1.94 lei per piece is quite a lot. And this is if we buy 50 pieces or more. That's basically around 40 cents or so. Yeah, it might not sound like much, but compared to all the other options that I will present to you, it is. And bear in mind that this is just for the positive versions. If you want to buy the negative voltage regulator versions, the prices go up incredibly. Like I haven't bothered actually searching for them, but I know that they are like 3 times more expensive. They are close to $1 per piece, which is like it's a bit crazy. Anyhow, this is LM317, okay? Probably the most popular voltage regulator on the market. Another one that I guess nowadays is not so popular anymore, but as far as I understand, it used to be more popular. It's LM723 or Micro A723, because there are two versions on the market. Nowadays you get more with Micro A than LM, but anyway, these are other integrated circuits that were specifically designed for use in power supplies. The advantage is that with this chip, you have more flexibility in the design process, because, you know, unlike with the LM317 where you have only 3 pins, the input, output, and an adjustment pin, this chip has many pins. It has a reference voltage that is separate from an op-amp, that is also separate from some transistors. And based on how you connect each of these components within this chip, you can basically create a power supply or another. You can have certain adjustments or certain other adjustments. You can make... anyway, it gives you some more flexibility in the design process of your power supply, which of course is a good thing. However, as a disadvantage, well, it's not so simple to use. You have to understand this integrated circuit, the internals of this integrated circuit, which is not difficult, but you know, it's more difficult than the 317. It occupies more physical space because, of course, we're talking about a chip with many pins around, and you are required to connect several pins to several more components on the outside, okay? And it also costs a lot more than 317. It costs 2.48 lei per piece if you buy 100 of them, so basically around 50 cents. Not 50 cent a wrapper, just 50 cents money. Anyway, and that is if you buy 100 of them. This is considerably more than even the 1 amp version of the 317, and you only get a maximum of, if I remember correctly, 150 milliamps. So around the same performance as the small power 317, except more than it's about twice and a half the price for that, which is a bit too expensive. Sadly, I would consider this a nice choice for certain projects if we would be able to adjust the current, the maximum current. But sadly, we have only some basic possibilities to adjust the maximum current. We can only create more like a current limiting circuit that makes sure that the output current does not go beyond a certain threshold. But we would have a problem actually, designing, actually using this chip to control the output current and to basically create a constant current mode power supply instead of a constant voltage mode. So overall, I do not see enough advantages for 723 chip to be able to actually recommend him. Okay, so thinking about these two very popular chips, I have reached the conclusion that, well, actually we could use some tricks with some other chips, and we could actually, replace any of these two chips, 317 and 723, and we would actually get more bang for the buck, how you guys say it, at least in America, as far as I've seen. Anyhow, let's take a look at an entire series of chips called 78L something, where what comes after that something designates the output voltage. We would also have 79L somethings, which would be the equivalent of 78 but for negative voltages. But again, we will be discussing about positive voltages only for the sake of simplicity. Also, I have chosen to discuss only about the 78L05, which gives us 5 volts on the output, for simplicity's sake as well. There are some other variants that provide 9 volts, 12 volts, 15 volts, even more, but you will quickly understand that it doesn't really make sense to buy those so much. So these ICs, these chips are in a way similar to LM317, with the exception of the fact that they are predetermined to have a fixed output voltage. So instead of having an input output and an adjustment pin, they have an input output and a ground pin. So you're supposed to connect that pin to literally the ground of your circuit. So on the input you have certain voltages, on the output you have a fixed voltage, in this case of 5 volts. Of course, there are certain requirements like having at least 2 volts more on the input, and yeah, I'm not getting into the details because again, that's not what this video is all about. You're also recommended to have an input and output capacitor. I've left them out because I'm not talking about that. So what are the advantages of such a chip? Well, it's simple to use. Again, just like LM317, maybe even simpler, because you only need that chip and nothing more. Some optional capacitors, but you need those for pretty much any solution, so this is why I left them out. You've got a small physical space. I mean, what can be smaller than a single chip that has 3 terminals? And the 100 milliamp version, which is the only version that I care about, costs very little. It costs 0.23 lei a piece if you buy 100 pieces of them. So yeah, I mean, sure, you do get a fixed voltage, but 0.23 compared to 0.93, yeah, it's kind of 4 times cheaper. Okay. So definitely an advantage. Now these chips also come in 1 amp versions, which obviously cost more, but I do not care about them, and I will show you soon why I do not care about looking at them. Like I don't even care to consider about them. The only downside to this is that you have a fixed voltage. If you care about having 5 volts, if that's all you need, perfect. If you can get with, if you can satisfy yourself with 100 milliamps maximum, again, perfect. You just use this IC, this chip, and you don't need anything else. However, if you cannot work with this fixed voltage and you need a higher voltage, well, it depends a lot on how much higher. If you need anywhere between 5 and 7.5, and I will explain in a moment why 7.5, if you need anywhere between 5 and 7.5, you can use just a simple trick. And instead of connecting the ground pin directly to the ground, you can use one or more diodes, and you can basically make use of the fact that any diode will keep a certain voltage across her while a certain current is passing through her. And of course, that voltage depends on that particular current, and sadly depends on temperature as well. But anyway, leaving that aside, this is a simple trick that you can use to basically take a 78L05. It works with any other model, but I'm sticking to L05, which gives 5 volts between the output and the ground, just for the sake of simplicity. You can use such a trick to create slightly higher voltages. For instance, if I put a 1N4007 here in the ground pin, I will get a roughly 5.6 volts on the output of the entire circuit, because the chip himself makes it so that the 5 volts that he regulates are between his output and his ground, right? Because he cannot possibly measure voltage between other 2 pins. So if you lift up his ground from the actual ground of your circuit, then you will have a different voltage on the output, right? And this is simple. So you can use any combination of diodes here, Schottky, rectifier, or even Zener diodes, to create a different output voltage. The advantages are that it's still a simple to use circuit. It's still a small physical space. It doesn't take a lot of space because, again, we only have 1 or 2 diodes, depending on the case, depending on what voltage you need on the output. And this brings us some possibilities of voltage adjustment. Of course, we cannot do fine adjustment. We can only do adjustments in steps of these particular dropout voltages on each diode that we place here, but we still have some possibilities of adjusting the output voltage, okay? And we still get to have the advantage of the price, because, you know, the cheapest 78L05 still costs 0.23 lei a piece, which is basically 5 cents, right? So let me see, if I divide 0.23 to 4.5, yeah, 5 cents, okay? And a diode costs even less, 2 cents and something, like 0.16 lei a piece. Again, if we buy 100 of them, but at these prices, yeah, we will certainly want to buy large quantities of them. So all in all, we can get away with a power supply that is, you know, around 40 cents or so, which again, it's still cheaper than 0.93 lei for the LM317. Now, let's say that we want finer adjustment of the output voltage, and we also need voltages that are higher than 7.5 volts. Well, then we can use a TL431 chip alongside a 78L05. A TL41, for those of you who don't know, is behaving like an adjustable Zener diode, but with much better results. It's got temperature compensation, it's got a much tighter tolerance for its dropout voltage. It's much better than any diode that we could use like in the previous examples. The only disadvantage is that TL431 has a minimum voltage of 2.5 volts, right? So in combination with the 5 volts of the 78L05, we get a minimum output voltage of this particular circuit of 7.5 volts. This is why I mentioned earlier that threshold of 7.5 volts. So this solution is still simple to use. I mean, you still have 2 chips and 2 resistors here. Like, they don't occupy that much space. I have placed here a potentiometer because I have played on the breadboard with a potentiometer to be able to just freely adjust the output voltage. But in reality, when you will want to build such a circuit, you will want a fixed output voltage, and then you will just calculate what resistor ratio you will need here, and you will choose 2 resistors accordingly, right? So you will have 2 chips and 2 resistors, which I would say it's still simple to use. It's still a relatively small circuit. You have plenty of voltage adjustment possibilities, because with such a circuit you can go from 7.5 all the way to 41 volts on the output. Why 41? Because TL431 has a recommended maximum output voltage of 36 volts plus the 5 volts of the 78L05 equals, right, 41 volts. So I would say this is a pretty big deal. And also you have the advantage of the price. So if you buy the semi-dev version of the TL431, because this chip comes in 2 different versions that sadly cost different money. If you buy the semi-dev version, then both of these chips will cost you 0.52 lei, okay, which is about 10 cents, which is still cheaper than the smallest, the cheapest LM317, which is 0.93 lei. And if you buy the through-hole version of the 431, you will pay 0.81 lei a piece if you buy 100 of them, which is still it's still cheaper than, you know, 0.93 lei for LM317. So we still get the advantage of the price. The only downside is, like I said, the voltage is adjustable only from 7.5 instead of 1.25. But in the vast majority of cases, this is not a problem. And the flexibility that we get, in my opinion, is worth a lot more. Because sadly, you cannot use LM317 for anything other than a power supply. However, you can use the L431 in a vast array of other circuits that do other things. You can use them in switch mode power supplies. You can use them as just voltage voltage references in all sorts of other circuits. So basically, by making a personal stock of 78L05s, which can be used in many other situations as well when you need another power supply, and TL431s, you get a lot more flexibility of basically choosing what to do with these components rather than with 317s or with 723s. And you might say, yeah, but you know, we can only go up to 100 milliamps. Well, not really, because you can still employ the same trick as with, you know, any 3-terminal voltage regulator by just using an extra power transistor, bipolar transistor, with an extra resistor placed like this. You would use something like this for LM317 as well when you would want to go above the 1 amp limit. So again, you want higher current, perfect. Just use basically this circuit with an extra resistor and PNP, bipolar transistor for positive voltages, or NPN for negative voltages, and you have the same benefits. Like you have all the benefits from the above example, with flexibility, with voltage output adjustments, and you still get the benefit of the price, because all of these three things, the both chips plus the bipolar transistor, would cost 1.05 lei a piece if you buy the 431 in the SEMEDE version, or 1.34 lei a piece if you buy the 431 in the through-hole version. Okay? And this is still cheaper than LM317. Like, this is crazy, but it is what it is, you know? I mean, okay, 1.05 is technically speaking a bit more expensive than 0.93, but I mean, come on, you get more than 100 milliamps of current, you know, and here you have 1.94 lei, which is still more expensive than 1.34 here. So, and needless to say, you have again the same high level of flexibility. But the 140 or 139 are just general purpose transistors that you can use in all sorts of other situations. Whenever you don't need to use them in a power supply, just use them anywhere else. Okay, like I said, 431 chip, you can use him in many other situations, and 78L05 basically can be used standalone to have 5 volts, or in all of the combinations that I've shown above. So here the only serious disadvantage is that there is no over temperature protection on the transistor, so you will have to make sure that the transistor doesn't overheat and basically burn himself and transform himself into a short circuit, which will then throw everything you have on the input all the way to the output and potentially damage the rest of the circuits. But anyway, that's a different problem. Technically speaking, even though they say that LM317 does have such a protection, you should not really rely on her, because this protection, if I remember correctly, this protection starts to become active around the temperature of 160 or 170 degrees, which is way too high anyway. So I'm like, yeah, even if theoretically we would have a protection in that chip, we shouldn't use that. We shouldn't rely on that anyway. So my point is, it doesn't make sense to buy larger quantities of 317s or 723s to have them in stock for future usages. For future use, it makes a lot more sense to just buy a larger stock of NPN medium power and high power transistors, and NPN and PNPs, well, bipolar transistors, buy 78L05s and TL431s, and that's it. And you can just create any voltage out of these that you might potentially want and need. Honestly, as far as I've seen so far, I've never used any voltage that's in between 5 and 9 volts. So yeah, what can I say? By the way, this whole trick with raising the potential of the ground pin of the 78L05 works because the 78L05s make it so that a current higher than 1 milliamp flows through this ground pin of theirs. I have tested several of my chips and they all basically want to consume about 3.6 milliamps of current from the input through the ground pin. And this is a high enough current to make any TL431 work, and even discrete diodes work as well. Just in case you were wondering how come this trick works, yes, it works because these three terminal power regulators, they actually need a what is called a quiescent current, right? And this quiescent current is big enough in order to power other circuits like TL431. So this is the big conclusion that essentially I wanted to show you. I wanted to share it with you because basically from now on I will just stop thinking about LM317s and 723s. Now, granted, I might still want to have some 10 or 20 pieces in stock of 317s, you know, just in case I might want to, I don't know, fix a device where they used a 317 and it's broken, and yeah, it makes sense for me to just replace that broken 317 with a new 317 and not complicate myself by having to redesign that power circuit, you know. But other than just a few such components, I wouldn't buy LM370s anymore. I would just buy 431s, 78L05s, and medium power and high power bipolar transistors. Now, I have shown you everything that you needed to know with regards to this first situation that I mentioned earlier, when you want to just power a certain circuit with a constant voltage and you don't care about anything else. Regarding the second situation, when you actually want to have adjustable voltage and current, I have thought of a circuit that I have actually tested earlier on a breadboard. Now, I'm presenting to you the circuit only as a sort of like a proof of concept. I would do some further testing and improvements on him, so don't take him and just use him as he is. It is good enough to a certain degree, but again, certain improvements would need to be done. The idea is that we can have circuit with adjustable voltage down to 0 volts without any tricks like obtaining a negative voltage and having an adjustment pin connected to that negative voltage, like without any crazy shit like that. And we can also have an adjustable current so that we can switch this whole power supply in constant current mode by essentially decoupling the power transistors that pass power, they connect the input to the output, decoupling them. Basically these transistors act like a switch, decoupling this switch from the control circuit, which can be created by using just common op amps that have a input common mode range that can go down to 0. And that can be a very cheap and abundant LM324 that we can just buy in hundreds of pieces, right, from the market. And we can get away with just a single chip. We would have to use all 4 op amps that are, you know, LM324, but we don't need more than 4, so we can get away with just a single chip we need basically a reference voltage, which in my tests I have for which in my test I have used a Zener diode, or just a regular Zener diode. Of course, it has some disadvantages. So in a high precision circuit, I would actually use a voltage reference integrated circuit, right? Not just a Zener diode, but anyway, that's besides the point. We need a reference voltage in order to obtain two adjustable reference voltages, one that adjusts the output voltage and one that adjusts the output current. We would feed these reference voltages into two different op amps that would basically one would compare the output voltage and would determine if he would need to shut down this switch, this Darlington pair transistor switch, based on whether the output voltage went higher than what it needed to go. And as well as another op amp that basically does the same but with a current. It monitors the current that is flowing on the output of this power supply circuit and determines if he needs to shut down this Darlington pair switch because the current has gone above a certain threshold, right? That is adjusted with these potentiometers here. So these op amps basically turn on an NPN transistor each, which in turn pulls down to the ground the base of this Darlington pair, and by pulling the base down, they essentially shut down, or they diminish the voltage to the point of actually shutting down the Darlington pair and therefore the output voltage. We need a third op amp in order to measure the output voltage with a shunt resistor on the low side, on the negative power rail essentially. I have used a 0.1 ohm shunt resistor, which basically gives us a 100 millivolts per amp. This is a bit too low voltage for us to use. We would like to use a 1 volt per amp, so we need to basically multiply this by a factor of 10. So we have a third op amp, non-inverting op amp, that literally does just that. It takes the voltage from the shunt resistor and amplifies it by a factor of 10 and feeds this measurement voltage in the other input of the op amp that handles current regulation. And the second input of this op amp was connected to the potentiometer with which you can adjust the current. The output voltage would normally be able to be sensed directly from the output of the circuit, which is the emitter of the Darlington pair. However, we would have a bit of a problem because the output voltage that the op amp senses would be able to sense in this way would be would be the output voltage plus the voltage on the shunt, which is dependent on the current. So in other words, the circuit that we would power with this power supply would get a diminished voltage the higher the current that he draws from this power supply is, right? Because the higher the current, the more voltage drop we have on the shunt resistor, and therefore the more the output voltage drops. In order to compensate for this, I have created another type of compensation circuit with another op amp, another transistor that acts like a switch, and a couple of resistors, 100 ohm resistors each. They do need to be exactly the same value, and well, in this case, they need to be 100 ohms. The idea is that whenever we have 1 amp on the shunt resistor and therefore 100 millivolts, This circuit will make sure that we also get 100 millivolts on R12 here, okay? Because if you take a look at this op amp has the plus input on the output of the shunt resistor and the minus input on this particular resistor here. So he will make it so that the R12 voltage relative to the ground will be essentially the same as the shunt resistor's voltage. Okay, but if we have 100 millivolts for 1 amp of current across a 100 ohm resistor, then we would have a 1 milliamp of current flowing through here, and this 1 milliamp of current is also flowing through this upper 100 ohm resistor, which will develop a voltage that is equal to the voltage on R12, which is equal to the voltage on the shunt resistor. So essentially we have mirrored the voltage on the shunt resistor, but relative to the positive side. So now if we feed this as a voltage for our voltage comparator to compare with the reference voltage, then this circuit will be able to compensate for whatever voltage we have dropped on the shunt resistor. Essentially, the more current we have on the shunt resistor, the more the whole circuit will increase the total voltage, so that the voltage strictly on the output will remain constant. Okay, this is why we need 4 op amps, but it's not a problem because there are 4 op amps, there are the so-called quad op amp integrated circuits, like LM324, which is dirt cheap, okay? And again, compared to LM317 or 723, with this circuit, we can actually get a voltage adjustment down to 0. We can also get a free current adjustment, and yeah, it cannot get better than that. The only disadvantage is that we need to provide some filtering on the output. I've done some tests with no filtering whatsoever, and the circuit kind of oscillates, at least on the breadboard. With 1 microamp capacitor on the output, the oscillation is not so bad, but it's still there. With 10 microamps, it's almost gone, but not quite. Sorry, 10 microfarads. Sorry. So we're talking about the output capacitance of this capacitor. So it's microfarads. If I said microamps, you know what I'm talking about. Anyhow, so I would say that you need to do some tests for yourself, depending on, you know, the output current that you want to have and the voltages that you want to work with. So you will need to determine how much bigger this capacitor needs to be. And this is a requirement, unlike LM317 and, you know, other chips that don't really require such an output capacitor. But honestly, I don't consider this to be such a big problem for, you know, the huge advantage of having adjustable voltage down to 0, adjustable current, and the overall flexibility to do whatever else we want with this circuit, because we can work inside the circuit however we want. In fact, I recently showed you basically a charger for lithium and lead accumulators that was in essence very similar to this circuit, except it was a bit different. I was using comparators instead of op amps over there. I was using a different voltage measurement circuit. Anyway, things were a bit different, but the principle was the same. Okay, so yeah, to quickly list the pros and cons, like I said, the advantages are voltage adjustment goes down to 0, has current adjustment too, so it can work in constant current mode, and can be built with almost any op amp and or bipolar transistors, provided that the op amp the op amps can go down to 0 or volts on the inputs. They don't have to be rail to rail, but they need to be the so-called ground sensing op amps or something like that. You know, the input voltages need to be able to go down to 0. The disadvantages are that, well, the circuit has increased complexity, right? You have a whole bunch of components around here. It requires filtering capacitor on the output, and this filtering capacitor needs to be of proper size. And for stability over temperature, it requires a proper voltage reference instead of a Zener diode. But again, I would say that the flexibility that we get is pretty huge. So this was pretty much everything that I wanted to show you and all the conclusions. And now you get to decide for yourself if you think it's worth buying more LM317s, or if you will consider this trick with the L431, 78L05s, and some transistor like BD140. So, thanks a lot for watching. I hope you have found this useful and informative. Make sure to hit the like button and perhaps even subscribe to the channel if you would like to see more. I will definitely come with more videos in the future to, you know, advance some more in this work of trying to prepare ourselves so that we can handle electronic work in the future by, you know, making a stock of components right now in the present moment while we still can. Again, thanks a lot for watching. I will see you soon in the next video. Bye bye.